Okay, so here are some more ratio test examples. For our first example, notice it's similar to one that we already did, but the powers are a little bit different. We've got n up here and 2n plus 1 over here, as well as a factor of n plus 1 on the bottom. So I've written the thing up there in case you guys forget. But what I'm going to look at is, again, the ratio an plus 1 over an. Since everything's positive here, I'm just going to ignore, well, I'll write this, but I'm not going to write them again. Okay, so one thing about this business is that you have to be, it's easy to mess up with these powers. For the n plus 1 term, I'm putting in n plus 1 for n, right? So that's easy here. I have to be a little bit careful. It's 2 times n plus 1 plus 1 in this situation, okay? So that's that term. I'll clean it up in the next step. And then for my reciprocal an, and again, because I'm doing the n plus first term, this guy is n plus 1 plus 1. I wrote it directly as n plus 2, but you can write that also as a separate thing if you like. So anyway, here's this. I'm going to clean it up a second with that mess there before I start canceling stuff out. So this is 2n plus 2 plus 1, so this should be 2n plus 3. And over here, I've got n plus 1, and I've got 4 to the 2n plus 1, and then I've got 10 to the n. So now, what cancels out? This 10 to the n cancels that n, so I have 10 to the 1. This 2n cancels that 2n, so technically I've got 4 cubed and 4 to 1. I'll just leave it that way. Okay? So here I've got 10. Well, you know what? I'm going to put the n plus 1 in front. So I've got n plus 1 times 10 times 4 over n plus 2 times 4 cubed. Well, I can get rid of one of those. And I could have gotten rid of it there too, but I just thought maybe it would be easier. Okay, so what do I have? N plus 1 times 10 over n plus 2 times 16. Okay, so now that I take limit of that. Out of space again, but we can surely stick it down here. I can pull out the 10 over 16 there if I want. When I take the limit of n plus 1 over n plus 2, I'm going to get 1, right, because 1 over 1. So I end up with 10/16 or 5/8 less than 1. This series converges. Okay. So a little bit just to be thinking about it. Again, this term doesn't make a huge difference. This is 4 and 10, so you might think, oh, 10/4, that's bigger than 1, but in fact it's 4 to the 2n. So it's really 16 as the n part in my R. So just sort of be careful with, it's very easy to mess up with these little things and then you'll get the wrong answer. You know, like I did in the previous video. All right, so this is the sort of standard one for that. Now, one thing we haven't done yet is an example with a factorial, and the ratio test is particularly good with factorials. So I'm going to do a couple of examples with some factorials. And you'll see why the ratio test is so helpful with factorials. It's very similar to the way things cancel out so nicely with the exponentials because of the ratio, right? So let's remember about factorials, first of all, before we do this. N factorial means n times n minus 1 times n minus 2 all the way down to 3 to 1, right? So n plus 1 factorial is n plus 1 times n minus 1, etc., right? So what is particularly useful with these is if I notice, well, this here is just n factorial. So if I want n plus 1 factorial, I can write n plus 1 times n factorial. Okay? So we will use this often. If you don't want to, you can just write it. Things cancel out, and that's fine. The other thing you have to be careful of, though, with these series is sometimes they'll have weird factorials. So, for example, sometimes you'll see something with 2n factorial, okay? So, but what does that mean? It means I start with 2n, and then I keep going down. So I would do 2n minus 1, 2n minus 2, all the way down to 3, 2, 1. Okay? And that's fine. I'm just illustrating it because it's easy to get confused. That is not the same as, for example, let me think. So sometimes you'll see stuff like this. 2 times 4 times 6 times 8 times 10. Okay, this is not 2n factorial, right? Okay, because 2n factorial has all the odds and the evens, even though it has 2n here. So it is not correct to write this as 2n factorial. All right, because as you see, like it would actually be, so that's why if you want something like this, odds or evens, they write it out specifically like that. Okay? Because once I have the factorial really means take that number and multiply it by everything underneath it. So odds and evens alike. So if they want only odds, only evens, only powers of 3, whatever, they have to write it out specifically. And if you see it written out there specifically, don't make this mistake because you'll get the wrong answer. And we'll do an example like that later in this video where it's something weird written out like that. Okay. So in the meantime, for this example though, I only need this thing that's in the box. So back to this example with a very straightforward n factorial. I'm going to put an plus 1 over an. Again, my absolute values aren't doing anything in this case because it's a positive series. N plus 1 term, n plus 1, 3 to the n plus 1 over n plus 1 factorial, n term. 1 over n term, right? Okay. So here you see, if I rewrite this with that formula, this is n plus 1 times n factorial and 3 to the n. So look at this. This factorials cancel out. This 3 to the n cancels out. Looks like this stuff cancels out too. N plus 1 cancels out. So I end up with what's left. I have a 3, and in the bottom I have an n. Okay? So now what happens is I take the limit as n goes to infinity of 3 over n, I get 0. Beautiful. 0 is less than 1. This converges nicely. Okay. So it's perfectly okay. Oh, by the way, you do have to be careful with this kind of thing. We'll talk about that more in the next section. But for ratio test, of course, 0 is just fine. For ratio test, 1 is the number which makes the test go bad, or doesn't give you enough. Okay, so I promised you one kind of crazy looking one. There's some crazy factorials. So let's do some crazy factorials. It's not really a factorial. This is one. I wrote this down from the book. They give you a bunch of terms. 14. And this guy is 5, 8. Okay, plus, dot, dot, dot. Okay. If we think about this as n equal 1, n equal 2, n equal 3, and n equal 4, what I need is my nth term, right? So that's the first thing I have to figure out. These are all going up by 4 at the top, right? 2, 6, 10, 14. So I want to do, want me to start from n equals 1? Yeah, I'm going to start from n equals 0. I don't like n equals 1, it's harder. It's harder for me. Let's start with n equals 0. That's fine. Doesn't matter. Because what I can do then is the top is going like 4n plus 2, right? So n equals 0 is 2, n equals 1 is 4, is 6, n equals 2 gives me 10, n equals 3 gives me 14. Okay? And then my bottom is going like 3's, right? 5, 8, 11. So 3n plus 5. Okay. But really, so my nth term, though, as I said from the previous little thing, I can't just write it. It's not like 4n plus 2 factorial. This is 4n plus 2 factorial. I have all the other intervening terms in there. So what I really have to write is I have to write it like this. I go for the nth term, I do that multiplication all the way up to 4n plus 2. And for the bottom term, I do this multiplication all the way up to 3n plus 5. Okay? So that is what my n term is. My arbitrary nth term, starting, of course, from n equals 0. Now, if you want to start from n equals 1, you have to do it with n minus 1 here. I don't know, it's just easier for me to write it that way. Anyhow, but you can do that too if you want. Anyway, so whatever. So there's my n, an. Now I need to do an plus 1 over a. Okay, so what do I do with an plus 1? Right, so what's going to happen here for, if this is an plus 1 is the exact same thing, only with one more term. So I'm going to write out, so I don't confuse myself, all the way to the an, and now I'm going to log on my next term for an plus 1. Okay, same thing here, 5, 8, oh boy, I'm going to run out of space. Okay. So this whole thing is my an plus 1 term. I'm going to have to like erase and do it up there in a second. And then my an term is just all the way up to here. And so I have the reciprocal of that, right? 11, 14, all the way to the 3n plus 5. And here, so it's basically exactly this, right? 2, 6, 10, 14, all the way to 4n plus 2. Wait, so here's the magic, right? The magic is that it's just like a factorial because you're multiplying all this thing. So all of this crap cancels out. All of these are the same as all of these. And all of these are the same as all of these. So the only thing I have left is this business. All right? Let me rewrite this. Get rid of this. Get rid of this. And the problem is that you can't do it easily like writing it out as factorials, but you just have to, when it's something mucked up like this, you just have to write out the terms and then realize as you write them out are what you're actually going to get. So let me rewrite it up here. I've got 4n plus 4 plus 2. And then here I've got 3n plus 3 plus 5. Okay. Now when I take the limit, you have this guy. So this is just going to be 4/3. So it turns out that this series does diverge. It's hard to maybe see that from the beginning. Yeah, good fun.